Now we want to take a look at molality as our next concentration unit, and there's some key differences. There's still moles per solute on the top, but on the bottom we have kilograms instead of liters, and we have solvent instead of solution. Now the third is what's key in terms of their experimental application. Molarity is temperature dependent. Solutions expand and contract, which means the volume changes, and hence the molarity changes. Molality, on the other hand, because it's a count of moles in kilograms, which is a mass, is temperature independent. And so it can find its little niche of applications because of that advantage. Like molarity, molality can be used as a conversion factor, but you're not likely to see it. I've not seen it very much, but it definitely can be used. And to make it, all you need is a balance, and you carefully weigh out your solvent and solute, mix and stir. You do have to be careful though, because you're dealing with liquids, and liquids spilling on a balance, an electronic balance, is not a very good combination. So in terms of the care with making solution, that's your biggest caution. Now let's look at a little reminder. Here's our little mole. Molality is the little m. And what we would say if we had 0.125 little m, we might say that we have a 0.125 molal solution. Instead of saying a 0.125 molality solution, we shorten that a little bit. Only difference is molar and molal between the two. So you want to be careful with that. Let's take a look at an example. We have a gas additive called methyl tertiary butyl ether, 0.45 grams and 6,000 grams of gasoline. And we are granted discussing gasoline as a single substance, which is not true, but I wanted to have something that was interesting and applicable. Now, since this is present in the greater amount, if it was water, it's automatically water. In this case, you take the one present in the greater amount, it's our solvent. And since we have mass, I'm going to use my one step that molality is mass over molar mass divided by my kilograms of solvent. Be very careful going back and forth between kilograms and grams. 0.45. If you look this up, this is C5H12O, and its molar mass you would calculate to be 88.148. You have to go to at least 2 decimal places when you're using these. Rounding, especially with molar masses, can lead to some very wrong numbers in your final mathematics. So I get 8.5 times 10 to the minus 4th molal, which is very, very small. It's a small additive. It's not your bulk desired component. Now, if we talk about ions, we have molarity of ions, and you could do the same for molality. It's quite common to need to be able to measure the amount in terms of the ions present. When strontium nitrate, and remember all nitrate salts are soluble without exception, when it goes into water, you're going to end up with 3 hydrated ions: a strontium ion, a nitrate ion, and another nitrate ion. It's like they all came to a pool party and swam away from one another, and they're all surrounded by water. They're hydrated ions. This question said, find the molarity of the nitrate, is what I was doing here. And there's 2 nitrates. You simply need to look at the subscript in your formula to know that. And we multiply by that mole ratio, 2 moles of nitrate per 1 mole of strontium nitrate. And we would get 0.300 molar nitrate ions. If we'd wanted strontium ions, you simply have to note that my concentration, we'll use those brackets for molarity a lot. It's the symbol meaning molarity, that my strontium ion concentration is identical to my strontium nitrate aqueous. This would be once it's in the water, because that's a 1-to-1 mole ratio. Now let's take a look at one more example. We're looking at the total molality of ions. We have potassium is +1, phosphates are -3, and you know what my saying is about knowing your polyatomic ions. You have to get those down to memory. Now in this case, I'm going to end up with 1, 2, 3 potassium ions and 1 phosphate ion. We've used this symbol I before, and we're going to see it again soon. I is equal to the number of particles in solution. Now it's a little bit simplified view. It's not always exactly 4, but that's all we will deal with. So if it's ionic, it's the number of ions. If it's a covalent substance, then I is always equal to 1. So in this case, we'd have 0.250 moles per 1 kilogram, and that's of K3PO4. And we're going to multiply that by the fact that there will be 4 moles of ions, because it said total ions, per 1 mole of the K3PO4. And we'd get a 1 molal solution of our ions. Our next video will move into mole fraction.